going to start the lecture on advanced reaction engineering. So, in this class we will discuss about the multi-phase reactors, that is basically slurry reactors. So, in these reactors already we have discussed in our previous class, that is how to means what is called slurry reactors, how does it works, and various type of resistance that is developed in the slurry reactor. So, that we have discussed. So, now considering those equations or correlations that we have discussed in our previous class, based on that we will discuss few numerical problems. So, how to solve any slurry reactor problem where gas, liquid and solid phase are there and reactions is going on. So, that we will discuss. So, here's one or two examples we will consider, example example 1 and example 2. So, that basically we will discuss. So, in this by solving these examples numerical problems, so we can get an idea about there are various resistance, means in the gas phase resistance, absorption resistance, diffusional resistance, that is external diffusion, internal diffusions. So, how much amount of the catalyst that we have to charge inside of the reactors for a specified conversions, that for a slurry reactor. So, that basically we will discuss. So, here in our previous class we discussed about that surface reaction controlling is the one of the surface reactions controlling is there, and when particle size does not affect in the diffusional rate. So, then we can say that the systems, means the catalyst and the reaction system that we have taken, there is surface reactions resistance, and for that we have to consider is very small particle for the reactions, means particle size whatever we have taken we have to reduce into smaller size of particles. So, by that way we can eliminate the surface reactions that is controlling for these reactions. So, if particle size means resistance that is directly proportional to the particle diameter dp to the power 1. So, then we can say that it is internal diffusions is there, and that is controlling the reactions for slurry reactor reactions, and for that also we have to decrease the particle size for that particular system. And even if we see that the resistance RC that is directly proportional to the power of 1.5 to 2, then we can say that external diffusions is controlling, and then we have to stirring, means stirring speed or the stirrer that we have to use for this particular slurry reactors, the speed of the stirrer we have to increase. By that way we can eliminate the external diffusions resistance for that particular systems. Okay. So, these are the things we already have discussed in our previous class. Okay. So, and if we plot RCR against dP, then the resistance equations is coming when slope equals to 0 is like this, when slope equals to 1 then it is coming like this, and when external diffusion is there, when at that time the slope is 1.5 to 2 and the curves will come like that. So, now one example we will consider and we will discuss for considering slurry reactors. Let us say this is the gas phase reactant and this is the liquid reactants that would be there inside of the reactors, and catalyst, solid catalyst will be charged, and then this is the product maybe. So, these are the reactants, gas, another liquid, and catalyst, that is the solid. Product is also we can say it is a liquid product. So, now if we consider a slurry reactors, and from the bottom of the reactors we are passing the gas at a particular rate, that may be any particular partial pressure we can maintain, we can pass that reactant A or hydrogen from the bottom of the reactor, and in the reactors there we are considering where means solid catalyst is there and liquid, another reactant, second reactant is there, that is present inside of the reactors. Then bubble formation should be when bottom gas is entered inside of the reactors, bubble formation is there, and then 3 components are there and reactions will proceed at a particular temperatures that is required. So, let us say for this reaction 121 degree centigrade is required if we conduct these reactions in a slurry reactors. Okay. So, now in this particular systems the particle size that we have taken, or we can consider for this particular reactions, that may be 10 micron to 100 microns. Within that range, that particle size or catalyst particles that we have considered, that may be within that range. So, now we have to decide, means if we consider a specific particular size of, let us say 40 micron or 60 micron or 80 micron of particles of the same catalyst is available. So, if a specified particle size of that catalyst if we use for these reactions, then how much quantity we have to take for these reactions. So, that we can means calculate for this particular systems. So, let us say these reactions we have conducted, and the experimental data that we have, experimental data that is we generated from these reactions. So, by considering one by one run, let us say for run 1 means first time we are conducting the reactions by maintaining hydrogens, that is 3 atmospheric pressure hydrogen are passing through this reactors. Okay. And the solubility of these hydrogens is given 0.007 kilomole per meter cube, and the catalyst particle size we have considered 40 micron for run 1, and the catalyst that was charged 5 kg per meter cube, and corresponding rate was evaluated, that was 0.0625 kilomole per meter cube per minute, that is the rate of the reactions for run 1. Similarly, same catalyst means 40 micron catalyst particles, that is the particle size you have taken, we have charged for run 2. Run 2 means again separate run we have conducted, and then 40 micron catalyst particles they have taken, and then we are maintaining the hydrogen pressure, that is the 6 atm, and corresponding solubility of hydrogen should be increased. Of course, as pressure is increasing, the solubility of hydrogen in the liquids that would be higher, and based on this Henry's law. So, here, so if we multiply it with H with partial pressure that was taken, so then the concentration of the hydrogens we can find out using these correlations also. And for 40 microns the catalyst was charged 0.2 kg per meter cube, and corresponding rate was this. So, similarly for run 3 also we have taken 80 micron catalyst particles. So, earlier 2 was run 2 40 microns, here 80 micron catalyst particles, same catalyst, but catalyst particle size is different, that was taken, and that amount 0.16 kg per meter cube amount of the catalyst that was charged inside of the reactor. So, and here the pressure was maintained, that was 6 atm for this run 3 or that reaction, and corresponding rate is evaluated, that was this. So, this is the experimental data that is given for this particular reaction hydrogens and liquid reactant that would take place in a particular slurry reactor, where catalyst charged at different particle size and different amount, and corresponding rate are evaluated. Now, we have to determine, this is the question 1, that is the controlling resistance. So, we know controlling resistance, there is surface reactions control, internal diffusion or resistance control, external diffusion control. So, which one would be the rate limiting step, and how much means controlling resistance for this particular system or reactions in a slurry reactor, that we have to evaluate. And number 2 is the, if we use 80 micron of particle size, what are the various percentage resistance to the absorptions on diffusions, that will be means percentage resistance of individual resistance that we have to evaluate once we have charged 0.4 kg per meter cube of the catalyst. Okay, so, 0.4 meter cube means that is the unknown quantity in between 5 and 0.2 kg per meter cube, in between that amount of the catalyst when we charged. So, then what would be the resistance for 80 microns of the catalyst particles. Okay. So, that is the unknown. So, that these are the things we have to evaluate from this problem. So, here first we will start with means Henry's law is given. So, Henry's law is given, H bar equals to partial pressure of hydrogen equals to concentration or solubility of hydrogen in the solutions, that we can find out. H prime is given. So, for run 1, so concentration of hydrogen for run 1, if you want to find out, you have to multiply it, the H prime is there with partial pressure 3 bars, 3 atms, that we can multiply. Then for run 1 the concentration of hydrogens we can get this is the concentration of hydrogens for run 1. So, now Ci by minus R hydrogens, that we have to find out, and for that, since R is given, this R value is given, R of rate of reactions for hydrogen is given for that particular points for run 1, let us say for run 1 it is given. So, Ci value from the Henry's laws we can find out, and this is the this, and rate that is given in that data. So, we can find out Ci by minus Ri for run 1. Okay. So, that value would be this, it is coming this. So, once we put this value and that rate equals to 0.0625, this is the rate of hydrogens, so that is rate of reactions for hydrogen that is disappearing due to the reactions that is given. So, if we divided this with rate of the reactions, that it comes this value. So, and M, that is the catalyst charge, that was also given 5 kg of catalyst charge for this particular run 1. So, if we inverse that, so that would be 0.0 meter cube per kg. So, similarly for run 2, run 3 also we can find out Ci by minus R hydrogens, and 1 by M we can find out, for run 3 also we can find out. So, now we have the 3 different consecutive run 1, 2 and 3, we have this and this value. So, now if we plot, so x axis 1 by M and y axis Ci by 1 by minus R H2 if we plot. Here see run 1 and 2, that is the 40 micron particles. So, if we plot this value 1 and 2, so then for 1 by M is this, and 1 by M another run 2 is this. So, then for one value this, if 4 points if we plot, then for 40 microns, let us say this is 40 microns. So, 40 microns it is coming this, and for 80 micron particles if we plot, it would be like this. So, for two different particles, different size of the particles, if we plot this, so then the nature of the curves would be like this. From this graph we can say that 80 and 40 micron size of particles, it is behaving different. Okay. So, now from this graphs we can get intercept, and this is the slope, and this is the intercept. Okay. Slope equals to, we have discussed in our previous class that RCR equals to RR plus RC, that is equals to slope, this by this equals to slope. Slope we can get that some numerical value will come for 80 micron particle, or similarly 40 micron particles also that value we can get, and intercept both the particles in the, since the gas liquid solid system are the same. So, here's the absorptions RAB that is coming, RB that is equals to coming this. Okay. So, if you know this numerical value RB we can find out, and now see here's, if we want to get the slope for 40 micron particles, 40 micron particle. So, it is coming RCR equals to the slope, it is coming this. If we want to calculate the slope for this particular point, known value x and y value is known, for this particular also point x and y value is known. So, once we know this, then the slope equals to this. Similarly, for 80 micron particles also. So, this equals to, it is coming this. So, then the total resistance for 40 micron particles and 80 micron particles is coming this and this value. So, if we do a ratio of those two resistance or the slope for two different size of particles, for 80 micron particles and 40 micron particles. So, 80 micron particle, this is the 40 micron particle, the resistance we obtains for 80 micron particle 0.283, and for 40 micron particles this. So, if you do the ratio of them, so it is coming 2. So, it indicates that the resistance for 80 micron particles, that is almost double of 40 micron particles. So, if we conduct the reactions by considering 40 micron particles, the resistance that we will get for the internal diffusions, external diffusions or absorptions, the whatever the diffusion resistance will develop or will get for this particular system, and instead of that if we consider 80 micron particle the same catalyst, then the resistance will be double. Okay. So, it indicates that means catalyst particle size and resistance means see 40 and 80, that is the catalyst particle size almost double. So, resistance is also almost double. So, it indicates that resistance directly proportional to the diameter of the particles. So, particle diameter is 40, the resistance will get, and similarly if we double the diameter of the particles, the resistance will be double. So, it directly proportional. So, it comes in this category, in the second category. See here when we have studied or derived the different type of resistance that is controlling for these reactions for slurry reactors, we have said that if slope equals to 0, then surface reaction is controlling. If slope equals to 1, then internal diffusions is controlling. If slope equals to 1.5 to 2, then external diffusion resistance is controlling. So, now it is coming in this category, means when 40 to 80 micron particles we are using. So, then the systems is following this, means internal diffusions is the controlling resistance. Okay. So, from here we can get. Okay. Therefore, what we have to do, if we know this, in this case we have to decrease the particle size. Therefore, to decrease the resistance, smaller catalyst particle size should be used. So, once we know either these three which one is controlling step for this particular system. So, here from here it is said that internal diffusions resistance, that is the controlling step for this particular catalyst or catalytic system. So, here if we want to eliminate the resistance then or decrease the resistance, then we have to use a smaller catalyst particles size that we have to use. Okay. So, now we have to find out the percentage resistance for 80 microns particle size that we have taken, and that was charged 0.4 kg per meter cube. That amount of the catalyst was charged for 80 microns of particles. Then percentage resistance we have to find out. So, how to find out percentage resistance? So, this plot already we have for 80 micron of particles. So, this is for 80 micron particles we have. So, from here intercept slope already we have find out, intercept from the graph we can find out that particular point would be the RB, that is the absorption resistance that we can find out. So, if from the graph if we plot 1 by m against this, so then for 80 micron of particles RB is coming 0.08 minute. So, that is the constant for this particular 80 micron particle size. So, gas absorption resistance. Okay. For the amount of the catalyst we considered here 0.4 kg per meter cube. Okay. 0.4 kg per meter cube. So, here 0.4 kg per meter cube of the catalyst. So, 1 by m equals to 2.5 meter cube per kg, and 2 meter cube would come in this particular region. So, in between 2 and 3 2.5 is coming. So, if we draw this line, it interact with the 80 micron particles, these lines, and then we can get it here. So, then from the y axis that is 0.84, that is the total overall resistance for that amount of the catalyst 0.4 kg per meter cube 80 micron particles that we have used. So, now it is coming 0.84. Okay. So, then the total resistance or overall resistance is this, and absorption resistance is this. So, if we already know that the for this particular systems internal diffusion resistance is controlling, there is no external resistance that is not controlling. So, only internal resistance diffusional resistance is there and gas absorption resistance is there. So, gas absorption resistance that we are getting from the graph equals to 0.08, and total resistance that we have evaluated from this particular point, that was 0.84. So, if we divide this by this multiplied with 100, then 9.5 percentage that resistance that is developed for the gas absorption, that is 9.5%, and then internal diffusion resistance that would be rest of that that was in our particular system. There is no external diffusion resistance is available within this particular size of the catalyst that we have used. Okay. So, now it is clear. So, how to find out percentage resistance for this particular gas, liquid, solid systems, that we are using a particular catalyst particle size and particular amount of catalyst, means 0.4 kg per meter cube of the catalyst that was charged for this particular systems. Then individual resistance we can find out from graphically, and also we can say which particular resistance is dominated and what percentage. So, here from here you can see that the value it is 90.5 percentage, means most of the resistance is coming from internal diffusion resistance, and gas absorption resistance is 9.5 percentage, close to 10 percentage, and it is close to 90%. Okay. So, that way we can say that. So, means resistance is dominated for this particular gas phase reactions, gas, liquid, solid, means multiphase reactions in a slurry reactors. Next, another example we will consider, example 2. So, here also we are considering, let us say this is our reactions gas and this is our liquid catalyst we are conducting placing inside of the reactor. So, here this is the product methyl oleate. So, that is the liquid phase products. So, in this particular reactor volume is given, that is the 2 meter cube, slurry reactor volume that was given 2 meter cube, and molar flow rates of liquids, that is molar feed rate of methyl linoleate, that is the liquid product in the reactor is given, and Fa naught equals to 0.7 kilomole per minute, and hydrogen pressure that was charged here from the bottom of the reactor, that was 6 atm, and gas phase absorption resistance that is also given 0.08 for this particular system. So, now we have to calculate the catalyst charge necessary to achieve 30% conversions using 60 micron particles. Okay. So, here 60 micron particles means earlier one we have discussed by considering 40 micron particles and 80 micron particles. Now, we are considering 60 micron particles, and here conversions we need 30%. So, then how much catalyst we have to charge in terms of mass, that is m that we have to calculate, other components are known. So, then step by step how to proceed this, here pressure is given. So, these pressures we can put it here, then the solubility or concentration of the hydrogens in the liquids that we can find out using this Henry's law. Okay. So, here concentration of or solubility of hydrogens in that particular system is Ci equals to 0.04 kilomole per meter cube, that is coming from equations. Okay, Henry's laws. Next, this is the same problem. In same problem here this data is given, means catalyst particle size and rate of the reactions and catalyst how much quantity that would be charged. For these 3 runs it is given. So, already 40 and 80 micron particles we know, but here particle size is 60 microns, that is the unknown parameter, that is not given in this data. So, if we prepare the catalyst, that particle size is different than earlier 2 known value, means 60 microns, that is unknown. So, with that particular particle size, if you are able to make that catalyst particle, then how much quantity of the catalyst you have to charge inside of the reactor to get a 30% conversions. Okay. So, that m values basically we have to find out m. Okay. So, now from these tables we can similarly we can plot Ci by minus r H2 versus 1 by m. So, we can run for 40 and 60 micron particles, these runs and this value we can get, and then we can plot similarly as we did for 40 micron particles and 80 micron particles, and Rb is also given 0.08 minutes, that is the gas phase absorption resistance is given, and from the slope also we can get Cr for 80 microns and 40 micron particles each, that is this. This is also we have evaluated. Similarly, if we plot them means ratio them Cr 40 microns, Cr 80 microns, that we are getting this. It says that Cr RCr, that is the resistance due to the diffusion, internal diffusions, external diffusion and reactions, that is equals to directly proportional to the diameter of the particles. Up to this we have done. So, now for 60 micron particles RCr means that slope we means 80 and 40 micron particles we have developed, but for 60 micron particles we do not know. So, that we have to develop or we have to find out how to calculate RCR for 60 micron particles. Okay. Since here the resistance, total resistance, that is directly proportional to the diameter of the particle. Since 80 micron particle is known, 60 micron particle is known, resistance for 80 micron particle is given. So, then 60 micron particles also easily we can find out. So, resistance for 60 micron particles, that is unknown, that you have to find out. From 80 micron particle resistance is given, particle diameter, that is directly also proportional to the resistance, directly proportional to the diameter of the particles, so that we can write this. So, now 60 micron particles, the resistance or slope would be like this. Okay. So, then it is coming by putting this value is known 60 by 80, 60 micron and 80 micron particles diameters that we know, that would be the ratio of them. Okay. So, then 60 micron particles resistance would be this. So, RCR we can find out. Okay. So, now we consider that reactors design equations. Here the reactor, the slurry reactors we have considered, it is a C star type of design equations at the we can consider for these systems. So, then if we multiply this equation, design equation here with solubility of hydrogens, if we multiplied by left hand side and right hand side. So, then the equations would become this. This is the design equation for C star reactor. Here multiplied both side, left hand side with Ci and right hand side also Ci, and after rearranging we can get this. See, in the right hand side Ci by minus Ra, that is this value is known for 60 micron particles or 60 micron particles, this we can write this. Okay. This correlations we have developed in your previous class. So, Ci by Ri or Ci by minus Ra, that is equals to gas absorption resistance into 1 by m into RCR, that is the resistance that is for due to the external diffusion and internal diffusions. Okay. So, now here see in these equations we can this Cr this we can substitute here. So, then this part equals to this part. Okay. Left hand side of this equation equals to right hand side of this equations by Ci by 1 minus Ra, that we are substituting here. So, then from these two correlations we can write that this equals to this. Okay. So, here we have to find out the M, that is the amount of catalyst that would be charged for this particular reactions to get 30% conversions. This is given. If you want to get 30% conversions, volume of the reactor is given, F naught is given, molar feed rates of component A, that is given, Rb also is given, that is the gas phase absorption constant is given, RCR also we have find out for 60 micron particles, that we can substitute here, and Ci is also given, that is the solubility of hydrogens for that particular points we can know. So, now if we substitute all these components, known component in these equations, then 1 by m we can find out, that is the unknown component, that is the mass of the catalyst that we have to charge for this particular reactions to operate and to get 30% conversions. So, 3.95 kg of catalyst per meter cube of the volume of the reactors or volume of the solutions, that amount we can or we have to charged. Okay. See, so catalyst charge means 5 kg we charged for 40 micron particles. So, here if we get 30% conversions, so for 60 micron particles we have to charge the amount of the catalyst, means these are the components are known, molar flow rate that is given, conversion is given, volume is given. So, this part means resistance part from known component means 40 micron particles and 80 micron particles, that value is given. So, unknown component, that is the 60 micron particles, that we can find out by using direct correlations. This is the correlations with this correlation. So, then easily we can find out what would be the resistance for 60 micron particles for this particular reactions, the same reactions if we change the particle size. So, easily the quantity of the catalyst that we have to charge for these reactions or to carry out the reactions, easily we can find out. Okay. So, now I think it is clear, means we have discussed two different numerical problems for considering different particle size, considering reactions in a slurry reactors, and then easily we can first we can find out the what would be the resistance and how much percentage is that from that slope and intercept, and after that by using other correlations or the data that is available, we can easily find out the controlling resistance and what percentage of each resistance that is means affect for this particulars, or this particular resistance has a role in controlling the reactions, means multiphase reactions in a slurry reactors. Okay. I think so now it is clear. So, the theory we have discussed in a previous class, and then the numerical problems, or from these two numerical problems the overall systems is very clear for us. Okay. So, thank you. So, today is up to this. I think in our next class at different reactors we will study. Thank you.